everyone. So first I would like to thank the organizers to give me the opportunity to talk about the joint work with Liza Marquand, where we are classifying all those finite directional symplectic action on OG10-type IHS manifold. It is very lattice theoretic, so today I will just focus on presenting some induced action, geometric induced action from cubic fourfold through the LSB construction that Tasha introduced already yesterday. And then I will talk about the lattice criterion to detect when those actions are coming or characterized via cubic fourfold. So just to fix notation, since we haven't used much OG10 up to now, when we have an IHS manifold which is of OG10 type, then the BBF form will be isometric to a fixed lattice that I will call lambda. And this fixed lattice is 3 copies of U, that we have the EH lattice, 2 copies of it, and the A2 lattice. And the A2 is like the E8 is the lattice associated to the thinking diagram A2. Okay, so for now that's the only notation I will fix. And I want to mention that I talk about finite birational symplectic transformation because we know by the result. So it's the name of the paper, symplectic rigidity, but I usually refer, or I guess many people refer to the symplectic rigidity for it, by Giovenzana, Grossi, Onorati and D Veniani from 2022. That says that, I guess Chiara mentioned it during the lecture, that if X is OG10 or OG10 type, then the only symplectic automorphism of X is the identity of X. So if we want to study symplectic action on OG10, we have to go in the birational world. We can't just, because we already know all the symplectic automorphisms. And we know that there exists a non-regular birational transformation. When you take a case-free surface, you have the original construction of Ogilvy, and if you have a symplectic automorphism on the case-free, it induces a symplectic transformation on the associated OG10. And so those one has to be non-regular, because we have the symplectic rigidity. Okay, but I won't talk about this construction. I will talk about the LSB construction from cubic fourfold, and later, for lattice theory, we will understand why for us it was more interesting, this one. So I will just briefly recall the LSB construction, and we will see first induced action and induced action. Is it big enough or not? I tend to write small on the blackboard, so just tell me if you can't read that on there. Okay, it's not readable at all. So we have seen yesterday that if we have a smooth cubic, then we have a vibration in abelian fivefold, du over U, where U is the open subset of a smooth hyperplane section of V, which we call the Donaghy-Marquand vibration, also called intermediate Jacobian vibration, because the fibers are intermediate Jacobian of some cubic threefold. And this guy comes with a zero section here. Okay? And what Laza, Saccà, and Voisin proved in 17, first for general smooth cubic, and then Saccà proved it in 2023 for cubic fourfold in general, then they proved that there exists a smooth IHS compactification XV. We call it XV of JU, which is OG10. So XV is of OG10 type. And it comes with a Lagrangian vibration, phi V, from XV to V5 to O. And this Lagrangian vibration extends the Donaghy-Marquand vibration we have there. All right. Yes. So what is important is I won't mention every time the LSV associated to V because there might be different compactification, so we can end up with different LSV from a V. But all these LSV, they have a common property associated to a V. We already know two classes in their neuroseveral lattice. Namely, we have a sublattice, which is generated by a class L, and L is the pullback of O of 1, pullback of a number class, and theta is the relative theta divisor, which is a kind of a closure of the union of the theta divisor on the Donaghy-Marquand equation. All right? And the point here is this is isometric to the hyperparabolic plane lattice. All right? So I recall that this is given by the gram matrix 0, 1, 1, 0 in a good basis. All right. And so this will be important because we will use the existence of this algebraic lattice for our lattice criterion. So, in the same paper, Saccà proved that, and this is where we have induced action, that if F is an automorphism of V, if F is an automorphism of V, then it induces birational transformation on any LSV. Okay, we have an action on the universal family of hyperplane section, and then we have an action that transports into the Donaghy-Marquand progression, and so we have a birational transformation on the LSV. Okay, and those satisfy very nice properties. So those properties follow mostly from the paper of Julia. They are not directly written, but you can find them if you easily. First, we know the action on the lattice, and the action on the lattice fixes the copy of U, the same copy of U. So each induced action will fix the pullback of the amper class and the relative theta divisor. The relative theta divisor. Okay. Then if you investigate a bit more the action on the lattice, you will find that, I don't know how to note it, but AF at, so the natural action of the isometry F on the discriminant group of the lattice is trivial. Okay. So in the case of OG10, the discriminant group of the lattice is a Z over 3, and so it has two isometries, plus or minus the identity, and all induced action will act trivially on the discriminant group.
So that is H2. Or...
Yes. It's the H2 for any OG10. And yes, and what I'm missing is that if F is symplectic, if and only if F hat is symplectic. So symplectic on cubic fourfold, you can see it as symplectic on the Fano variety of line, and we have actually also the same equivalence here because we have an rational isometry between the transnatal lattices, and so you can compare the action on the symplectic form. All right, and actually what we prove is that here that's actually enough to characterize the action on the lattice. So, in particular, if we have a group of symplectic birational transformation acting on OG10, and in the invariant lattice we find a copy of U, we can deform it and find a birational model for which we can characterize the action from the cube. So maybe it's not clear said like this, but I will state it right now. So if X is an OG10, and we have G, a subgroup of symplectic birational transformation of X, which is finite, and with trivial discriminant action, so trivial action on discriminant group, that, okay, for an isometry I do A little f, here I will do J bar. I hope it's not too confusing, but, so this is a subgroup of O of A lambda, and this one is trivial. Then we have an equivalence. Then the invariant part of the lattice contains a copy of U if and only if the pair XG is determined. So when I say determine is exactly what I did. So up to deforming and finding a birational conjugate model for the pair is determined by the pair XV, JV. XV is an LSV associated to a cubic fourfold with JV, a group isomorphic to V. So as an abstract group, they are the same one, but this one is coming from a group of symplectic automorphism on the cubic fourfold. So this works nicely because we work with birational transformation. So we have, I would say, more flexibility when we work. So we are using information on moduli space and especially on the deformation theory. But at least we can obtain such kind of conclusion because we are working with birational transformation.
But in the theorem you write G bar is trivial, but doesn't it follow from the properties above?
Sorry?
The triviality of G bar in the theorem, doesn't it follow from the second property above?
No, second property is for induced action, but in the theorem I don't start with induced action, I start with any OG10.
Oh, okay.
But then I show that actually we can make it look like an LSB and induced action. All right. But thanks for the question, because then we have this assumption in the theorem where we work with trivial action on discriminant group. So we could think that maybe we are covering everything because maybe all action will be trivial on discriminant group. But as a note, Claudio Onorati showed that, so in the course of Chiara, we have seen that the image of the representation of the automorphism group or the birational group of birational transformation on the lattice as image, I don't know if you mention it like this, but as image in the monodromy group of the associated to the image of the monodromy group of X on the lattice. And Claudio Onorati showed that for OG10-type hyperkähler manifold, this is isomorphic to the group of orientation-preserving isometries. And this, if we look at the action on the discriminant group, it's full. So we can find element monodromies which act by minus the identity on the discriminant group. So the theorem a priori doesn't cover all the cases, and so what I will do now is try to show you that we can try to do some slight modification, especially on the LSB, to try to cover the other cases and find such kind of theorem. But for this I need to introduce a particular involution that exists on any LSB that we will construct from a smooth cubic, and I will call it the LSB involution tau. Are there any questions up to now? Or no? Okay. So, as before, we take V, a smooth cubic, right? And I remember that I said, and it's still written there, on the Donaghy-Marquand fibration, we have a zero section. So in particular, if we take XV and LSV associated to V, we have that there exists a well-defined birational transformation which acts by minus the identity on the smooth fibers. That acts by minus the identity on the fibers of the Donaghy-Marquand fibration by negative identity on smooth fibers. Right. And so for now it doesn't show exactly why it's useful, but as I did for induced action, I will give you some nice properties about this tau, and then we will see why we care about this involution. So we can look at the co-invariant lattice, and Julia Saccà showed that this fixes also the same copy of it. So it fixes the pullback of the ample class and also the relative zeta divisor, because the zeta divisor here, they are invariant by pullback by minus the identity. Okay? All right. Tau is not symplectic. This can be checked also on the Donaghy-Marquand fibration. The action of tau on the discriminant group is minus the identity. You can prove that, you can try to show by modifying a bit the argument of this theorem that if tau was acting by plus the identity, it will be induced from the cubic fourfold, which is not possible because tau for the Lagrangian fibration XV, pi v, is vertical and all induced action are just horizontal, moving the fibers. So tau cannot act trivially on the discriminant group. And by the same argument as I just explained about this verticality and horizontality, tau commutes with induced actions. So in particular, if I start with this time with a non-symplectic, for example, involution from the cubic, and I look at the induced action and I compose with tau, I will obtain a symplectic birational transformation with non-trivial action on discriminant group. Right? If f of p is non-symplectic involution, then, well, since tau and f hat will both fix the copy of u and the commute, we have that tau composed with f hat, so the induced action by f contains fix a copy on u on cohomology. Tau f hat is symplectic, right? Because they both act by -1 on the symplectic form, so the composition will act by +1. And the action on cohomology is non-trivial. Right? So we are almost at the same properties as before, but here we have this condition that was not satisfied before.
So this action by F, the fiber, right? So
they just move, yes, they just move the fibers around. At least the smooth fibers. Okay. And so this result was used implicitly by Laza Marquand in the first paper of early this year. So I will cite the paper and I will explain why. Where we show that, I mean, using this tau, we have been able to realize some symplectic involution on OG10, and we showed in a paper of the beginning of the year that there is this six classes of symplectic involutions on OG10. When I say OG10, I mean on OG10-type IHSM. Okay. Three of which are realized from a cubic. So from a paper of last year, Laza Marquand studied the involution on cubic fourfold, and she saw that they were not 76 exist. And there were like three classes of them, two non-symplectic and one symplectic. And they induce action, so we can look at the induced action, and using tau on the two non-symplectic, we're going to obtain three symplectic involution on OG10 that have different cohomological action. So those are three classes, and they were realized by Laza among a list of 4 that she found first, and then together we completed the list and find 2 exceptional using some more involved lattice construction. So first those were obtained not necessarily from the lattice, but some are obtained from the lattice, and 3 are realized from cubic. And we don't know how to realize the 3 others. We may know how to find one of them, but it's unsure whether it will work or not. All right, but more generally,
if you take a general X thing by elastic construction, what is the birational automorphisms of that? So it's just this involution, or there more?
There might be more. You may have.
For general.
You look at the automorphism of the general fiber, for instance, and you may obtain more. You may obtain more transformation, more birational transformation, for instance.
But if V is very general, probably there's nothing.
No, but so the thing is that if you have a V general from the first Laza Saccà Voisin construction, then all fibers are irreducible. And Julia Saccà showed that if the fibers are reducible, birational transformation that fix the ample class are regular. So, for example, in our theorem, we will find nothing. So for V general, you may have
no symplectic, but at least there's this one, which is ±1.
Yeah, this one exists. No, you can. It depends, because you have also rational translations on the from the translation on the smooth fibers. She made a remark about this in her paper about induced action, when she showed that in general we have more than just this one, but this one is particular.
There's no translation, right? I mean, the the model variable is model variable is equal to the primitive cohomology of the cubic fourfold is the rate.
Okay.
So you can, I mean, you get something of the infinite. Okay. That's the big.
Okay. Right. So, yes, thank you. But here, so I wanted to come back here. When I showed that this was symplectic, what I said is that this worked because the action on F hat on the symplectic form was -1. So we don't need F to come from non-symplectic involution, but at least we need that the square of F hat is symplectic. So more generally, and you write it here, more generally, if F is an automorphism of B, non-symplectic, but F squared is symplectic, then tau F hat will have the same properties as before. So we have all these properties. So I'll put these properties star, and here we may satisfy star. And in particular, in this case, the order of F is even, and tau sub F hat has the same order as F. Right. And so from this, we can actually show the same theorem. So I will just take the same theorem, but just change some parts of it. So we take still an OG10 with a group of symplectic birational transformation, but here we take G bar actually equal to O of A lambda. Okay. And we have an equivalence. G fixes a copy of U in cohomology if and only if the pair XV is determined up to deformation and birational conjugacy by a pair XV-JV, where JV is now still isomorphic to G, but a subgroup of automorphism, not necessarily symplectic, and the symplectic part of JV, symplectic, has index 2 in JV. Right. So you first take the part that acts trigger in the cohomology on the discriminant form, and you do the previous theorem, and then you use tau to transform a generator of the quotient, and you can obtain the similar kind of result. All right. So now I can.
So what's like in the last thing you will know?
So.
So
Yes. So JV, comma S for symplectic. And so it's the index of the symplectic subaction in the group as index 2.
So, because you're not supposing you're symplectic. Okay.
Yes, and so, yes. And since this, because this has only 2 isometries. Yeah. So if you take the action acting trivially, you take the quotient plus of the 2. All right. Now we show an example. So this is the largest example we have been able to realize geometrically, and it's coming from the most symmetric cubic fourfold, smooth cubic fourfold, so the Fermat cubic. So here V will be V of x0 cube plus, so just the cube of all the 5 variables. This is the Fermat cubic, right? It has a automorphism group of 170,000 and something. But for us, we will focus on how it is generated. So the automorphism group of V is generated by the symplectic action, a non-symplectic involution, and a non-symplectic automorphism of order 3. So maybe I will do phi 2 for the involution and phi 3 for the non-symplectic of order 3. All right? And we will denote H, the group generated by GH and phi 2. So if we look at the theorem or a construction, we can show that using the tau involution, any LSV XV associated to V, so the Fermat cubic associated to V, has a group H prime, which is isomorphic to H, and which consists of symplectic birational transformation. All right. Now we may wonder what's happening on the lattice side. So maybe as a remark here, So as an abstract group, we can look at this H as an abstract group, and we can look at all the possible up to conjugation birational symplectic action on the lattice, and it's unique. This action of H prime on lambda up to conjugation is unique. So this follows from our classification, and moreover, lambda H prime is isometric to U plus A to 3. And here we are happy, because our criterion supposes that we should have a copy of U in the invariant, and we have a copy of U in the invariant. So everything makes sense. All right. But then if we look carefully, I said that we still have a non-symplectic automorphism of other three here. And so in particular, if we take tau as the LSV involution, and we compose by induced action by phi 3, we get something which is purely non-symplectic. So it's non-symplectic and all its non-trivial powers are non-symplectic. Purely non-symplectic of order 6. And so basically what it means is that starting from the cubic, the paracubic, if we take any LSV, we can induce a part that will produce some symplectic birational transformation, and then another part that will give us a degree, an index 6 overgroup of it. And so at the end, we have that, this implies that XV has a faithful action by birational transformation, a faithful action of a group of order 2 times the order of OG. And this was expected by this existence of this term involution, right? And the fact that we have at least a non-symplectic automorphism of even order. And this is the maximal group we have been able to realize up to now. We don't know how to realize it at all. Do I still have some minutes, or I'm over the time? 1 minute? Okay, I just wanted to mention that so this is part of the big project that I told you where we're classifying group. We are still on the finishing of classifying. We have one little detail to do. But we have found, how to say that, more than 300 group, saturated group, and most of them are not geometrically realized. And especially we have what we proved to be the largest group acting on cohomology for any IHS manifold. Acting on cohomology because we have the kernel of the Kummer, which poses problem. And this we can't realize it geometrically. And if you want to realize it, it has a polarization of order 4, of degree 4, and it has 39 million elements. So if you want a little challenge to realize it geometrically, I would be very interested. And that's all. Thank you. The group is so you have this PSU43, if you know what it means. Then it admits a semi-direct product by with 2 elements, and this is a degree 6 extension. So this is the largest group of symplectic birational transformation, on cohomology that you can find, and it has and you can add something which is non-symplectic of order 6. And this has like order 39 million and something. But we know the lattice. So.
Can I ask about construction, right? So can you recover V from X? So if rational class of X is fixed, would there be more than one V? Like, I don't know. Is V?
Yes. I guess you can't expect to have V to be uniquely determined, except if you have a large group, because then we have a classification of group acting, and so maybe you can try to find a very particular V. Because we are working with isometry, we are working with symmetries. So if we have a lot of symmetries, then maybe we have less possible V's that satisfy the condition that we want. But then if you have a very small group, like a group with 4 elements, it's very likely that you won't have a unique V. Yeah, we have nothing constructive, so you can't, we don't provide the V. We just provide existence. Oh, you mean for the criterion or for the...
I meant in general in this LSV construction whether V is determined by X.
Ah, you start with V for the LSV construction.
Yeah, but like, can different V's, can different V's keep the same X?
No. Oh, I don't know.
I don't think so. In the periods of
There's some time. One, let's take our speaker.